Okay, so in order to derive the work energy theorem, so you guys can see where it comes from, we're going to take one of our kinematic equations and we're going to take Vf squared is equal to Vi plus 2a delta x, and we're going to solve this equation for delta x. So to get delta x alone, we have to subtract Vi squared to the other side and divide by 2a. Okay, so now that that's done, we know that our equation for work is going to be equal to F times delta x, or in integral form, this will be equal to F dx integral from xi to xf. Okay, so if we know what F is, and F is just equal to ma, and we know what delta x is, well, we can just plug those two in, and then we can derive the work energy theorem from there. So let's do that. So then we have that work is equal to ma Vf squared minus Vi squared all over 2a. And so then you can see very easily that you can cancel the a's, and that these two terms here, once we distribute the m and the 1/2 to each of the velocities, we can easily see that the kinetic energy here falls out. And so then this is kf, and this is minus ki. And then we have that our work here is just going to be equal to delta k. And so we have now derived ourselves the work energy theorem. So now in this case, this gives us another powerful way to determine the work, because we had this way at first, but now we have a second way of doing it. So we don't even have to look at the force given by a entity. We just need to, over a distance, we just need to look at the change in the kinetic energy. So one of the relevant examples where this is useful is, say you have just a regular plane, no incline, no nothing, and from there we have a box that has a mass m and is moving in this direction with some force F. Now it's a little blurry. I'm trying to unblur it. Anyway, this is a force F. And from this point, it has some velocity Vi, and over here now, it has some new velocity Vf. We can determine what the work done over this distance from xi to xf is over this interval. We can determine the work using the work energy theorem instead of using F delta x. So if these numbers here are not given, we can then go ahead and determine the work done. Another way that work is useful is when we're trying to learn like how much potential energy is stored in a compressed spring. So in a compressed spring, we know that the force with for a spring or Fs is going to be equal to Kx. So as you displace the spring by a distance x from its equilibrium point, and it exerts a force S proportional to its spring constant, K. So we plug in F into our integral equation. And so then a K is going to be outside because it's just a constant. We're going to have an X left in the inside, and then a dx, and we're integrating from xi to xf. So very quickly, we see that this integral of x is going to be equal to x squared over 2. And so then we have 1/2 k x squared from xf to xi. And then we can see that this is going to be equal to 1/2 k delta x squared. And so then this is going to be the work done on a spring as you compress it a certain distance from its equilibrium point. And conventionally, this is going to be equal to the potential energy stored in the spring. So why don't we do an example with our new quantities that we have just derived. So this is going to be a long example, and this is going to be a show of the power of energy conservation and how easy these equations fall out for even difficult problems. Okay. Give me one moment to find my other pen here I've been using. Like this. Okay, so for the situation we're going to be considering, we're going to have this wall with this plane here, and then an inclined plane tacked on at the end. There's going to be some angle theta here, and attached to the wall, there's going to be a spring with a platform attached to it, and on the end of this platform, we're going to have a box with mass m. From this platform here to here is a distance x. And then we want to find how far this box climbs up the inclined plane here. So first thing, so the spring is going to be compressed and then released. Then the box M is going to slide along this surface with friction. And that friction constant is going to be mu of k1 over this distance x. And then it's going to slide up this inclined plane. And this inclined plane has a spring constant mu of k2. And it's gonna go up this inclined plane of some height h. Okay, so first things first, we have to work with the box here and the spring to find out what its initial velocity is due to the spring being compressed. So we use our statement of conservation of energy. EI is equal to EF. And so this just says that our initial energy is going to be equal to our final energy. And so from here, what we can do is we can say that EI is going to be a composite of the kinetic energy plus the potential energy. And then EF is going to be a composite of the final kinetic energy and the final potential energy. So in this case, when the spring is being compressed initially, our kinetic energy is going to be equal to 0. And then when it is fully decompressed, our potential energy, or our final potential energy, is going to be equal to 0. Then all of the energy will be kinetic in this case. Okay. So UI is going to be this quantity that we derived here. And so then we're going to have on this side that 1/2 K delta X squared is going to be equal to 1/2 MV F squared. And so then we can easily just solve this equation for VF. And so then we can see that our 2's are going to cancel. We're going to divide the m to the other side, and we're going to take the square root. So then VF is just going to be equal to the square root of K over M, because we divided and took the square root, and then delta X. The square root cancels with the square on the delta X. And we saw that our 2's drop out. So we have now solved for our final velocity here. And so the next thing we have to do is we have to analyze the interval from x from when the box stops touching the spring to the edge of the ramp. So this is going to be our second interval that we're going to analyze over. And so we can do this a couple ways. We can use the work energy theorem like we did before in order to find this, which would just be the work done is just going to be equal to the kinetic energy. And so then we can say that you can do this 2 ways. You can use energy conservation, but you can also use the work done, and we'll do both ways. So then work is going to be equal to F times delta X, but this interval length is just going to be X. So we're going to leave it as Fx. And so then Fx is going to be equal to the change in kinetic energy, which is going to be 1/2 mv F squared minus 1/2 mvi squared. So the force here that this box is going to be experiencing is the force of friction. And so we can get the force of friction here is going to be equal to mu of K1 mg. That's all it is. And so from here, we can say that we can find the final velocity, because we can plug in this real quick. Mu of K1 mg is going to equal 1/2 mv F squared minus 1/2 mvi squared. We can easily see that the m's cancel, and that we can multiply it 2 to the other side, and then we can solve for VF here. I'm going to move this over here. F with friction is going to be mu of K1 mg. So we canceled our m's and we're multiplying by 2. So we have 2 mu of K1 g is equal to VF squared minus VI squared, and then VF is going to equal 2 mu of K1 g plus VI. Well, and this is all under the square root. But VI in this case is going to be our VF from our last part of the problem. And so then we can replace that in here, and we can say that this is going to be equal to the square root of Km delta X. So now we've solved for the velocity at this point here. So we know what V is here. But for the next part of the problem, it's going to be useful to know what VF squared is. So I'm going to tack the square back on, and I'm going to get rid of the square root for the moment. But we have found the velocity at that point. So if you were being asked a multiple part question, we would know what the velocity of this point is. We just need to take the square root of this, or the square of that term. Okay. So again, you can do this the other way using energy conservation, and you would just follow the procedure that we did before. We have EI equals EF, but in this case, both the potentials are still going to be equal to 0. Well, what does that give you? It gives you KI is equal to KF plus W, and then you would just have to rearrange. You just have to rearrange your equations, and then eventually your the same quantity is going to fall out either way. So next up, we have to find how far the box gets up this this ramp here. And so in that case, we have to write another energy conservation statement where EI is equal to EF. And now in this case, we can break this down into its components. KI plus UI is equal to KF plus UF, and this is going to be a minus W. So we have to add this negative term for work here, because this box is going to be losing energy as it goes up the plane. You can either have, so if we were to say that both the potential energies were equal to 0, like we had in the second part of the problem, you can just easily rearrange this to get that work is equal to KF minus KI, and that yields the work energy theorem. But in this case, we do have potential energy in this case, because we're going up the inclined plane. So we're looking for how far the box goes up the ramp. So at that top point in the ramp, the kinetic energy is going to be equal to 0. So then our KF is going to be equal to 0, because our velocity at that point is going to be equal to 0. At the beginning, as it's at the bottom of the ramp, UI is going to be equal to 0 because it hasn't been up the ramp yet. So then KI is just going to be equal to 1/2 M times 2 mu of K1 G plus K over M delta X. And now you see why it's useful to have VF, because we can just plug in this statement here and here. And so then at the top of the ramp, this is going to be equal, the potential energy here is going to be equal to mgh, but h doesn't describe how far it goes up to the ramp. It just describes its displacement via height. So in this case, we have to use trigonometry to find out what the distance is, d, that this goes up the ramp here. I just drew out a d here from these 2 points. So in this case, d is our hypotenuse, so that'll go on the bottom. H is opposite the angle, So we can put that there, and I'll use a lowercase h just to keep things consistent here. And so since h is an opposite, we use the sine function. So then when we solve for h is going to be equal to d sine theta. And so then we can easily replace that with mgd sine theta. And so now we have to do one more thing in order to get what our work is. So the work in this case is going to be, we can draw out a little diagram here. So here's our box. Here is mg or w. Here is going to be, we can say w1, and here is going to be w2. W1 is going to be used to find friction, and W2 is going to be the resistive force that pulls this box back down the ramp when it's at the top. Okay, so in this case, we can say that this angle here is theta, and W is going to be our hypotenuse. And so W1 is going to be our adjacent value. So then W1 over W is going to equal cosine theta. And so then W1 is just going to equal W cosine theta. Now W1 is going to be equal to our normal force here, N. And so then the force due to friction as this box climbs is going to be equal to F of F is going to be equal to mu of K 2 mg cosine of theta. Now we have other stuff that we have to address at this point, and I can erase some of this stuff now because we're way past this part of the problem. So we have what the force of friction is, and I'll write that up here because we've figured this one out. Okay, so then the force pulling it down the ramp, or the resistive force here, is going to be equal to W2. And so then W2 is going to be equal to W sine theta, because it's going to be the opposite here. And so then W2 is going to be equal to mg sine theta. And so then the work done over this distance then, or I know this is going to get confusing because we already have work as weight, but we'll just say we'll just say capital WQ is going to be equal to mg d sine theta. Because without friction here, there still is an example to be made of this situation here, not including friction, and this is going to be the work that you're going to get when you're looking for the change in kinetic energy. So then in that case where there is no friction, we can say that since Kf is equal to 0, and we're subtracting W in this case, we can say that the work done is going to be equal to the negative of the kinetic energy. And so then all three of those quantities are going to be, or the difference in this quantity here is going to be equal to this quantity here. So without friction, this still applies. So then we have that W is equal to mg d sine theta. And then we have that work due to friction is going to be equal to mu of k mg d cosine theta. And so then this is, you add these two together and then plug them in here for work. So now if we do that, let's add these together to get our big W, and this is going to be equal to mgd times the quantity sine theta plus mu of k cosine theta. And so then we can plug that in here. And so then from here, we're going to get that 1/2 m 2 mu of k 1 g plus the square root of k over m delta x is going to be equal to m. We're going to factor out a d out of the entire thing because that's the actual quantity that we're looking for. So then d times mg, and then this is multiplied by sine theta trying to see if I have this right. I do have this right. Okay, so what we did here with this extra term of W is we determined the change in kinetic energy, but then that kinetic energy just got stored in potential energy, so the work was equal to the potential energy there. So this is just going to be md times mg times sine theta, and this is going to be a plus mu of k2 cosine theta. I would be double counting terms if I included this here. And so then we can just say that d is equal to 1/2 times m times 2 mu of k1 g plus 1/2, or the square root of k over m times delta x, all over mg sine theta plus mu of k 2 cosine theta. And we can see that our m's are going to cancel here. And then I'm just going to move the half in here so that we have 2g times the quantity sine theta. And so then this is your distance. I know that was a mouthful, but I just wanted to show you how work energy theorem and conservation of energy can be used to solve these huge problems that are going to help us out substantially. Any questions there? Okay. So now we've seen how powerful energy conservation is for complicated systems. Now let's use it to tackle a simple system. Let's analyze a simple system of, we take a ball, we throw it up in the air, we want to find the peak. Peak is h. Velocity at the peak here is going to be equal to 0. We give it some initial velocity vi. Cool. This is just one of your two-dimensional kinematic equations. So we use EI is equal to EF. At the bottom, our potential energy is equal to 0. So then we just have Ki on the left side. At the top, our kinetic energy is equal to 0, and we only have potential energy. So UF. So KF is equal to 0 over here. So next up, all we have to do is we substitute in 1/2 mvi squared is equal to mgh. We can see that our m's canceled and that h is now equal to vi squared over 2g.